Hello, beautiful people. Here's chapters 19 and 20. So now we're getting to the heart of microbiology. Chapter 19 is gram-positive microorganisms, and chapter 20 is gram-negative. We've actually gone through a lot of this stuff already. So a lot of chapter 19 hopefully will feel like review to you. But I feel compelled to cover it because doing so should help you with your quiz, with your assessment. Okay. So without further ado, here's chapter 19, gram-positive bacteria. Okay. And you should start feeling bored right now because here we go, going back to Staphylococcus aureus and Staphylococcus epidermidis. Okay. They're the main scourges that we have to deal with. The thing that I like to introduce this with is the fact that the name Staphylococcus describes the microscopic morphology of the microorganism. So staph means that the organism grows in clusters. So in fact, it's supposed to be Greek for a cluster of grapes. Okay. Then we have the linking vowel O, and then we have coccus, which means a spherical. Okay, so as you can see this picture, this looks like a little bunch of grapes. Okay, so that's your staph, and it is in fact spherical in shape. So Staphylococcus aureus and epidermidis, they both have the same microscopic morphology. Okay, what do we need to know? We need to know that they're facultative anaerobes. What does this mean? This means that they can either use oxygen or not use oxygen in their energy demands. Hopefully you know that using oxygen means that we're going through glycolysis, Krebs cycle, and the electron transport chain, and that not using oxygen implies that the organism can live on simple glycolysis. Okay, it is non-motile, in other words, it doesn't have any flagella, and it doesn't have any cilia, so that there's no way for it to move. It is salt tolerant, and the reason it is salt tolerant is because our sweat is rich in salt. So consequently, this gram-positive organism is not susceptible to osmotic pressures. This is important because this is one of the labs that I just updated today. Okay, it deals with the susceptibility of osmotic pressures by microorganisms, and the argument that we're trying to make is that gram-positive organisms, because of the thick peptidoglycan cell wall, are less susceptible to osmotic pressures of the environment. So because the surface of our skin is high in salt, it is considered to be a hypertonic environment, and that's why gram-positive microorganisms such as S. aureus and epidermidis feel right at home here because their thick cell wall protects them from this hypertonic environment. The same peptidoglycan cell wall prevents it from losing moisture to its surroundings. It does not allow it to be susceptible to radiation, heat. Another thing is that if you touch anything in the environment, it's actually possible to pass Staphylococcus aureus from one person to another environmentally. What does this mean? It means that it can reside on fomites, on wound dressings. It can reside on clothes. It can reside on blood, things that we leave behind as patients, okay, fomites. And that organism, again, if we don't use proper precautions and proper aseptic technique, the microorganism can be passed from one patient to another. Again, Staphylococcus aureus, if you guys remember the specific epithet, aureus means gold, and that's because when this guy grows on media, it turns a yellow or gold-like color. Epidermidis means that it lives above the skin. Okay, very easy. Both of these are part of our normal microbiota. However, if we become sick or we become immunocompromised or we become stressed, these are opportunistic organisms that will, given the opportunity, traverse the skin and cause disease, cause pathology in our bodies. Aureus is particularly troublesome. Your author tries to stress the fact that just a few hundred traversing the skin can cause problems. Okay, what are the virulent features of Staphylococcus? Well, it has the ability to have a glycocalyx that makes it difficult to phagocytize by your innate immune system. So that's one problem. It produces enzymes that allows it to protect itself on our body and to traverse our tissues. We're going to go into a couple of those in a second. And it also produces toxins that can that cause havoc in our body. So let's start with the defenses against phagocytosis. Okay, protein Staphylococcus aureus produces protein A. This is a protein on the surface of the cell, and this protein can be sloughed off, and it attaches itself to the epitopes of antibodies, rendering the antibody useless because it's not attached to the cell, it's attached to proteins that the cell is sloughing off. Okay. So this protein binds in particular to immunoglobulin G. Do we care? We care because immunoglobulin G is the workhorse of the humoral adaptive immune system. Okay, it is the immunoglobulin that's produced in greatest amounts for the longest time, with the widest range of effects on pathogens. So if we're rendering immunoglobulin G useless, that is a sincere problem. Okay. If the immunoglobulin cannot attach to the organism, then it cannot paint it for destruction or by consumption by dendritic cells. In other words, it is inhibiting opsonization. And because of this, it can also not launch the complement cascade. If you forget what the complement cascade does, one of the end events is to produce the MAC, or the membrane attack complex, which is supposed to destroy pathogens or bacteria by producing pores all around them. Okay, so if this immunoglobulin is not attached to the bacteria, then that complement cascade might be launched, but it's not going to target the bacterium because this antibody, this immunoglobulin, is not attached to the bacteria. So again, that produces a problem. And because dendritic cells and monocytes uses immunoglobulin G to attach to the pathogen, if the immunoglobulin G is not attached to the pathogen, then that renders the phagocytosis of that pathogen very difficult to come about. Okay, so in other words, if the immunoglobulin G is not attached to the pathogen, then dendritic cells and monocytes cannot find it, and that cannot phagocytize it, and therefore is considered an anti-phagocytic factor. Okay, so remember, if it's in red, it means that not only is it important, but you're probably going to be assessed on it on the quiz. What else do we have? We have bound coagulase. If you remember, the purpose of the coagulase is to make a blood clot around the pathogen, so that the innate and adaptive immune system cannot find this pathogen and be activated. So it's literally hiding it, evading the innate immune system, and consequently, the adaptive immune response. Okay, so that's significant. And then it also makes these polysaccharide slime layers. Okay, your author tells you that this polysaccharide inhibits chemotaxis of phagocytes. Again, we're talking monocytes and dendritic cells. And the reason for that is because the body does not recognize this polysaccharide as being foreign. Okay, so that's one problem. It also, that polysaccharide can also be described as a glycocalyx. And if you remember, one of the roles of a glycocalyx is to allow that cell to attach to each other, or to tissues, or to surfaces. Enzymes. We don't only have bound coagulase, we also have cell-free coagulase. and this causes blood clotting throughout the body. If it manifests sufficiently, then you end up with little blood clots throughout the body that are called petechia. This is not a desirable event. We have hyaluronidase. Hyaluronidase, if you remember, we've actually covered this before, but it's an enzyme that breaks down connective tissue, and it allows the bacteria to traverse the dermis and go into deeper tissues. And then we have streptokinase. So remember, the coagulase hides the bacteria, and then the kinase dissolves the fibrin. So once the bacteria, through some sort of quorum sensing, acknowledges the fact that there's no dendritic cells or monocytes near it, then it feels free to continue to traverse the tissues or go into the blood. And so it releases a streptokinase in order to dissolve those blood clots that it purposely produced around it. Okay, so these are some of the enzymes released. Additionally, we have lipases. Lipases are interesting. When we study the metabolism of microorganisms, we talk about the catabolism of saccharides, sugars, and the catabolism of proteins, amino acids. Rarely do we talk about the catabolism of fats or lipids, okay? And that's because fats or lipids are typically not an energy source for microorganisms. They're an energy source for us, but they're typically not an energy source for microorganisms. But Staphylococcus can use that as an energy source as well. So it releases lipases, enzymes that break triglyceride or fatty acids into simple molecules, so that those fatty acids can be additionally catabolized and used as an additional energy resource by this microorganism. Many of them produce beta-lactamase. Again, this is a review. If you remember, the beta-lactam ring. Let me see. You know what? Let's see if I can bring this up. I'm going to bring this over here. This is kind of fun. I like doing this. So the lactam ring. Okay. We'll do images. See that right there? That's a lactam ring. It's a little square, and this is a carbon. This is a carbon. Hold on, let me make it bigger so you guys can see it. So this is found in antibiotics, like penicillin, for example, has a lactam ring in it. Okay, so that's a nitrogen, of course. That's a carbon. That's a carbon. That's a carbon. That's a double bond and an oxygen. So this is called a lactam ring. And if you remember your chemistry, carbon does not like to make 90-degree angles like a square. It simply does not. It likes to make angles of about 109 degrees, and that's called tetrahedral if you remember your general chemistry. So what that means that this is a little my analogy is a little rat trap. Okay, you have a rat trap, and you have to put the spring on, and then it gets ready to catch the little rat, the mouse or rat. Same thing here. This square has ring strain on there, and it's not happy. So the trap is ready. Now what? Now this antibiotic is taken in by the microorganism. It tries to be incorporated into the peptidoglycan cell wall. And when it does that, the enzyme of the bacteria breaks that lactam ring, and it springs open, breaking the cross links between the sugars that are supposed to be producing that peptidoglycan cell wall. So effectively, you still have the sugars, you have the bricks for making the wall, but you just destroyed the cement, the cross-linking. Okay, so a lot of peptidoglycan targeting antibiotics have this lactam ring. As a fact, the majority do. Okay, so what? Well, the so what is that many Staphylococcus produce an enzyme called beta-lactamase, whose sole purpose is to break that lactam ring, rendering the antibiotic useless. It still gets taken in, but now that the lactam ring is not there, it doesn't cause any havoc. Okay, so break down penicillin. Okay, This allows the organism to live in the presence of antimicrobial drugs. And one of the things that your author tries to convey is that over 90% of Staphylococcus aureus are known to be penicillin resistant. So once upon a time, that number was very close to zero. Contemporarily, almost 90% of S. aureus makes the enzyme beta-lactamase. Okay, now we're moving over to toxins. Okay, these are toxins that are released. We've talked about this before. We've talked about exotoxins and endotoxins. Exotoxins are toxins that are literally released by the bacteria. Endotoxins are toxins that are inside the bacteria and only are released when the bacteria dies or is lysed. Okay, so these are exotoxins. These are released by the bacteria, and they're cytolytic. What does that mean? That means that the toxin literally kills the cells in your body. Cytolytic. To lyse means to break apart. So this is a toxin. See if I can make it big. This is a toxin that breaks cells. It's a cytolytic toxin. Okay. And what's even worse is that Staphylococcus aureus can also make leukocidin. And leukocidin is a toxin that causes the suicide, the killing of leukocytes or white blood cells. So in short, aureus can produce toxins that fight your immune system specifically. Scary stuff. Then we have this stuff called exfoliative toxins. So if you guys have taken anatomy and physiology, hopefully you remember that we have cells next to each other. There's two ways to hold cells together. One is called cell junctions, which are little proteins that go across. And then you have these really thick proteins that hold tissues together very, very well. Those are called desmosomes. And these exfoliative toxins literally target these desmosomes, causing cells to fall apart. Okay? And so you end up with superficial tissue sloughing off. And in this instance, in extreme cases, that's called scalded skin syndrome. Okay, as if you had been burned. There's scalded skin syndrome. Pretty dramatic. Okay. And then we have toxic shock syndrome. Toxic shock syndrome is a toxin that promotes anaphylactic shock. Okay, it can be in food, and it can function as an enterotoxin. Entero means gut, so an enterotoxin is a toxin that targets your gut, your intestine, specifically the large intestine. And when this happens, the main role of your large intestine, which is to reabsorb water from the bolus, ceases to function properly. Okay, what happens as a consequence of this? The individual ends up with diarrhea, and in extreme cases, this causes a problem because the individual's systemic blood system suffers as everything that they drink and consume comes out their bowel. Okay, so this can be a life-threatening event that can cause blood pressure to plummet. Forgive me, not plummet, to plummet. And again, this means that this can become an immediate medical emergency. Okay, things have to be done in order to keep this person alive. Typically, large bore IVs of normal saline to make sure that fluids are maintained in the body. Okay, so look at the contrast here. Here's Staphylococcus aureus, here's epidermidis. And notice that Staphylococcus aureus has everything we just mentioned. Epidermidis has a few things. And that's why if you have an opportunistic infection, chances are it's going to be Staphylococcus aureus, not epidermidis. Okay. let's see. One of the things that's important to know is that it's transmitted by direct contact or fomites. We covered this earlier. So that means that in a clinical environment, aseptic / sterile technique is very, very important in order to prevent the transfer of this infection from patient to patient, fomite to patient, instrument to patient, whatever. Okay. Let's see. This is impetigo. Okay. So in impetigo, you have a little scab on the top. There's still moisture underneath. The significance of impetigo, which happens in infants and children, is that the infant or child is very infectious at this point. So if one child ends up with impetigo within a very small amount of time, everybody's going to end up with it. So this is that's one of the problems with this. Okay, what's the significance of toxic shock syndrome? I already alluded to it. Is that it does the fact that it causes anaphylactic shock. Specifically, it produces fever, vomiting, rash, and low blood pressure. Okay, these can become this can become in a medical emergency. So that's important for you to know. Here's the rash that we're talking about. Okay, and this rash is brought about by the release of additional toxins by the organism called pyrogenic toxins. So we have to be careful. There's a word pyrogenic and there's a word pyogenic. They sound almost identical. Pyogenic means pus producing. Pyrogenic means fire producing. In other words, these pyrogenic toxins, once released into your body, have a tendency to go to your brain, going to reset the temperature setting on your hypothalamus, and your body reaches higher temperatures than it should. Okay, and consequently, you end up with these severe issues. Okay, let's see. It's probably important for you to remember these different manifestations of the pathology of Staphylococcus bacteremia when if it goes into the blood, which again is a terrible problem because that means it has become systematic. It can reach any part of your body. Endocarditis, we're going to hit that in just a second, but it's a manifestation in which the organism modifies the surface antigens in the inner lining of the heart and initiates an autoimmune response. Okay, pneumonia, when it reaches the lungs, the acidic environment of the lungs, and causes inflammation and the accumulation of fluid in the lungs. And subsequently, if that fluid continues to develop and attracts additional leukocytes to the area, then a pus begins to fill in the lungs, and that is really a problem. So that's empyema, pus in the lung, and that is a challenging event to resolve. And then finally, we have osteomyelitis, which is when the organism reaches the bodies of the bones. In children, this is usually in what's called the growth plates of long bones. This is where the problems take place. In older people, it's usually the vertebrae that get affected. And the significance of osteomyelitis is that it doesn't happen overnight. This has been an infection that has been around for a long time because it's hard to cause this problem in the bones. Okay, and additionally, once that infection takes place, it's very hard to get rid of the infection. So if osteomyelitis actually takes place, then the individual is going to be on antibiotics for quite a long time because bones are not particularly vascular environments. And so it takes a long time for the therapeutic effect of antibiotics to take place. So that can be a significant problem if it does manifest. What are we looking for? We're looking for gram-positive bacteria in grape-like arrangements. That's what the name means. Treatment, methicillin. If you have methicillin-resistant Staphylococcus aureus or MRSA, then vancomycin. And there is VRSA. There is vancomycin-resistant Staphylococcus aureus. And what do you do then? Well, then you're going to use a cocktail of antibiotics so that they can function against the microorganism synergistically. Okay. Okay, now we're moving over from Staphylococcus to Streptococcus. Okay, so where staph means bunches of grapes, strep means a chain. So Streptococcus is a chain of cocci or spheres. Okay, and we're starting with the last field, Group A, Streptococcus pyogenes, one of the really, really bad guys. Okay, like I said before, pyo means pus and gen means generate. So Streptococcus pyogenes is the pus generator. So that means that this is one of the bad guys. So what do we need to know? Well, if it goes to the pharynx and it causes inflammation or pharyngitis, strep throat, okay, not only does it inflame the pharynx, but if it's not resolved quickly, it can reach the heart or it can reach the rest of the body. If it reaches the heart, it can induce rheumatic fever, okay? And like I said, that's when Streptococcus pyogenes goes into the heart, attaches itself to the inner lining, and in particular the heart valves. It modifies the surface antigens of the heart valves so that they're no longer recognized by your own body. And then your body launches an autoimmune response against the heart antigens, consuming the valves. This is a big problem. You cannot have the valves of the heart be consumed, or your heart function goes down. So for a very long time there, if anybody was thought that they had strep throat, they were prophylactically treated with antibiotics immediately in order to prevent these very, very serious outcomes. Okay. The other one was called scarlet fever. Okay. And again, that's when that's a rash that starts in the chest and then continues to spread through the body. And the consequence of scarlet fever is a release of these pyrogenic toxins. Again, fire-producing or heat-producing toxins that go into your brain and reset that temperature setting in your brain. So it's important that pharyngitis, strep throat can lead to rheumatic fever and scarlet fever. That I don't know. Do I want to scare you? Streptococcus pyogenes is also the causative agent of necrotizing fasciitis. Okay, I'm not going to Google it. I want to stay professional here. Feel free to Google it on your own. And I warn you, what you're going to see is terrible. It is outright terrible because this is the so-called flesh-eating bacterium. Okay. And just because you have Streptococcus pyogenes doesn't mean that you're going to have a flesh-eating event. As a matter of fact, it's a very, very rare condition. We're not convinced that we know why it attacks some people and not others. There's been arguments about there being a genetic predisposition towards this, and there's been arguments about maybe lifestyle has something to do with it. So if somebody is an avid alcoholic and smoker and simply doesn't have good health to begin with, they seem to be more susceptible to necrotizing fasciitis or flesh eating. Okay, you and me, if we remain healthy, we might end up. It could be possible to get an infection of pyogenes and not come to a flesh eating event, if that makes sense. So again, it secretes enzymes that literally destroy the tissue, and it's a significant problem. If somebody actually has this, antibiotics is not enough. The necrotized tissue or the dead tissue has to be removed immediately and surgically and aggressively. Okay, so this is incredible stuff. In the glomerulus, okay, we're talking about the nephron of the kidney. If you end up with antibody and antigen complexes, we covered this in the last week, okay, then those complexes can accumulate in the glomerulus of the kidneys and carry out what's called glomerulonephritis, okay? It causes inflammation. It does not allow the proper filtration of blood through the renal corpuscle. And how do you know? Because it's blocking the glomerulus, less urine is eliminated, so you end up with a low urine output. You may end up with high blood pressure, and it is possible that allowed to continue, it can cause renal failure to some degree, okay? So like I said, Streptococcus pyogenes is one of the bad guys. Okay, what do we need to know? Gram-positive bacteria in short chains or pairs, hence the name. Let's see. And penicillin is the antibiotic of choice. Okay, not a surprise because we're dealing with gram-positive microorganisms. Let's see. What else do we need to know? Well, now we're moving to, we've been dealing with Streptococcus pyogenes. Now we're moving to Streptococcus pneumoniae. So pneumoniae, again, is diplos or chains. They're cocci. And they have attachment proteins specifically for the lungs and the bronchioles. Okay. It's important that to know that Streptococcus is catalase negative. Okay. Staphylococcus is not. Okay. How do we know this? Well, you guys just did it in lab. You guys just did it in lab. What do? You take a slide, you take a small inoculum of the microorganism, and then you add 1.5% hydrogen peroxide. If it bubbles, then the microorganism is catalase positive. If it doesn't bubble, then it's catalase negative. So you guys did in lab a diagnostic procedure that would allow you to distinguish between Streptococcus and Staphylococcus, okay? So again, Streptococcus are catalase negative, so that would mean that we add the hydrogen peroxide, no bubbling would take place, but Staphylococcus is catalase positive, so when we add the hydrogen peroxide, it would bubble, okay? So this is important for you to know. That's what pneumoniae looks like. Remember, diplos or chains. Okay, what else do we need to know? Pneumoniae has a polysaccharide capsule. I don't know if you remember what we used to call this. We used to call it a glycocalyx. What's significant of the glycocalyx? A couple things. First of all, the polysaccharide capsule is not easily recognized by our innate immune system. So it hides the microorganism from our immune system. What else? Well, it's poly means many, saccharide means sugars, which means that it's a sticky glycocalyx. So it allows these guys to, again, attach to each other, attach to tissues, attach to surfaces, okay? It also has a hyaluronic acid capsule, and this capsule does the exact same thing that this polysaccharide capsule does, and that's hide it from the immune system. So neither of these two are recognized by the immune system, and it hides the microorganism in our bodies, okay? So again, that's important for us to know. Now look at this. This is an incredible choreography, okay? So we're talking about Streptococcus pneumoniae. So we're talking the lungs. That's where this guy is going. First thing that it does was the first bullet point. It hides. It hides itself from our immune system. Then what does it do? It uses this protein adhesin. Now remember, this guy is going strictly for the lungs, where it only recognizes epithelium that is associated with the lungs. So that pseudostratified ciliated epithelium is necessary to keep all these microorganisms away from your lungs. That's what this microorganism is going to attach to. That's what it's going to recognize. So it uses this very specific receptor, this protein adhesin, and it binds it to the epithelium of the pharynx. Okay, what does your body do? Your body's trying to defend itself. What does your body do? Your body starts to secrete immunoglobulin A. The immunoglobulin A is supposed to attach to this protein adhesin so that this microorganism cannot attach to the epithelia of your lungs. That's the purpose of this immunoglobulin A that your body produces. What does a microorganism do? It produces secretory immunoglobulin A protease. This is an enzyme that is destroying the immunoglobulin A that is being produced by your body so it can attach to the tissue. Do you guys see how this is working? The bacteria does something, then our body does something to counteract it. Then the bacteria does something to counteract that, then our body does something to counteract that. It's kind of like a little tug of war. It's a little fight, okay? What's the next step? Well, the next step is that the bacteria produces what's called phosphorylcholine, and this phosphorylcholine does something very strange. It induces the phagocytosis of the epithelium. In other words, this epithelium consumes the bacteria. Epithelium is not supposed to do that. Not the ones in our lung. It's supposed to keep things out, not bring things in. So this phosphorylcholine of the bacteria induces the epithelia to phagocytize this bacteria, bringing it into our tissues. Finally, the bacteria releases what's called pneumolysin, which is again is a protein that lyses or breaks down cells of the lung. So what did it do? It hid from the adaptive immune response. It attached itself with an adhesin. It secreted immunoglobulin A so that adhesin will not be detached. Then it released phosphorylcholine so it can be consumed by your epithelia. And then it released pneumolysin to kill the epithelial cell that consumed it. What's it going to do next? The same thing all over again. It's going to attach IgA protease, phosphorylcholine is going to go in, and then pneumolysin. What is this thing doing? It is traveling through the tissues of your lung, reaching deeper and deeper tissues where it can cause even more pathology. It's incredible. Okay. So it can cause Streptococcus pneumoniae, not surprisingly, can cause pneumonia, okay, pneumococcal pneumonia. It can, in children, in infants, in which the eustachian tube is not very vertical. In infants, the eustachian tube is short and horizontal. So in infants, this Streptococcus pneumoniae can spend a lot of time in the middle ear and cause what's called sinusitis or otitis media, inflammation of the middle ear, okay? And that gives rise to the opportunity of additional opportunistic infections, okay? It can enter the blood, it can enter the heart, okay? What else? It can cause pneumococcal meningitis. This has been in the news. There's a lot of advertising about pneumococcal meningitis, okay? And the reason for that is because there's many different types of meningitis. However, pneumococcal meningitis is 20 times more prevalent than the meningitis caused by other microorganisms, okay? So 20 times higher, consequently, the mortality rate associated with pneumococcal meningitis is very high for infants. So this is very significant. Okay, diagnosis, gram stain sputum smears. Remember, these are all gram positive. It should be diplos or chains of cockeye. Quelling reaction, you don't need to know this. It's a antibody reaction in which if the streak of the microorganism swells, then we know it is confirmatory for Streptococcus. Okay, the treatment, penicillin. And now we're moving to the last one. This is Enterococcus. Entero means gut dwelling. Coccus, again, is spherical shape. This is interesting because we usually correlate gram-positive with being surface microorganisms, but this is a gut-dwelling microorganism that is still gram-positive. Okay, and there you go. You can see the chain of cocci. So this is Enterococcus. And it's important to know that it's a common nosocomial infection. The diagnosis, it is distinguished from Streptococcus pneumoniae by the fact that Enterococcus is not sensitive to bile. Okay, I know that this sentence is weird. This is the way that the author has it on here, but think about it. Enterococcus is a gut microorganism, and it is around the presence of bile. So therefore, Enterococcus is not susceptible to bile. By contrast, Streptococcus pneumoniae, which is not exposed to bile ever, is sensitive to bile. So this is important to know. And it's also important to know that Enterococcus is gamma hemolytic. Okay, so if you've forgotten what that means, you have that blood plate, and you have alpha, beta, and gamma hemolysis. Alpha hemolysis is partial hemolysis with a green sheen. Beta hemolysis is complete hemolysis. And gamma hemolysis means that there's no blood or erythrocyte lysis at all. Okay, so these two are the main ways of assessing Enterococcus. And with that, that's the end of today's little lecture. Thank you so much, and I'll see you guys soon.